Okay, maybe let's get started now. So hello, everyone. Welcome to the Speaker's Corner at the Virtual Science Forum. So I'm Chun-Xiao Liu. I'm currently a postdoc in Quantum Tinkerer Group in TU Delft. Today, I'm going to talk about one of our recent work, electronic properties of indium arsenide, European sulfide, aluminum hybrid nanowires. So in the talk, if you have any questions, just feel free to unmute yourself and ask directly. So yeah, this work is combines both theoretical and experimental studies. The theoretical part is mainly done by Delft group, including me and my colleagues Kostas, Antonio, and Michael. And the experimental part is contributed by our collaborators in Copenhagen, Sergej, Yu, and Peter. And you can find the preprint of this work on arXiv. Heterostructure between spin orbit coupled semiconductor and S-wave superconductor is a candidate for realizing topological superconductivity. So for one-dimensional hybrid nanowire, when the Zeeman field parallel to the nanowire axis is strong enough, and the chemical potential of the nanowire is tuned appropriately, the hybrid system will become a 1D topological superconductor, hosting a pair of Marana zero modes localized at Y ends. So one way to detect these Maranas is to measure the tunnel conductance spectroscopy in a normal metal superconductor junction. And the Maranas will manifest themselves as a quantized zero bias conductance peak in the conductance spectroscopy. And these Maranas are non-abelian aliens, so they can be utilized to make topological quantum computing. So far in most of the experimental studies, the Zeeman energy or the Zeeman field is induced by an externally applied magnetic field. However, this is not the only way to induce Zeeman energy in the system. So in a recent experimental study from Copenhagen, they studied a hybrid nanowire with some additional ingredient, that is the European sulfide layer. So this European sulfide is a ferromagnetic insulator and is expected to induce Zeeman energy in the hybrid system. So, and the supercurrent characterization of the superconducting aluminum layer indeed shows that there's some exchange coupling or Zeeman energy inside aluminum. So this is the extracted hysteresis behavior inside aluminum, and which is the role of this hysteresis behavior is played by European sulfide. So we note that even at zero magnetic field, there is still some finite exchange coupling inside aluminum. So then they measure the tunnel conductance spectroscopy in the NS junction for this hybrid device, and they find a zero bias conductance peak in a finite parameter space for this ferromagnetic hybrid nanowire, which is consistent with Marana's signature. And what's more interesting is that such a zero bias conductance peak is observed only in devices with a particular geometry. In some other devices where aluminum and the European sulfide do not have overlap, such a zero bias peak is not observed, in contrast with this successful device where aluminum and the European sulfide overlap with each other. So all these intriguing experimental measurements motivate us to ask two questions. So first, is it possible to realize topological superconductor in ferromagnetic hybrid nanowires? And if yes, what are the underlying physical mechanisms? And the second is, why is the overlap between aluminum and the European sulfide layer so important in achieving this? In the rest of the talk, I will try to answer these two questions. So here is a outline of this talk. So I will first introduce the concept of microscopic device simulation, and then we will explore different mechanisms for inducing Zeeman energy in the hybrid system. And finally, I will show topological phase diagrams for the hybrid nanowire. So first, microscopic device simulation. So this is a method we use to study the electronic properties of the hybrid nanowire. So in particular, we study the two-dimensional cross-section of this nanowire, assuming translational symmetry along the wire axis. So this is the effective Hamiltonian for this hybrid nanowire. Here we include both the indium arsenide and the aluminum degree of freedom and treat them on equal footing. And we treat the European sulfide in a phenomenological way. For example, at the interface between European sulfide and indium arsenide, we model this magnetic proximity effect by a local exchange coupling term. And when aluminum and European sulfide overlap, the magnetic proximity effect at this interface is modeled as a finite exchange coupling inside aluminum. So these two exchange couplings are the only tuning parameters in our Hamiltonian. And the other physical parameters in the Hamiltonian are fixed by known values. Another very important quantity in this Hamiltonian is the electrostatic potential phi here. It will determine the electronic density distribution inside indium arsenide. So in this work, we obtain this electrostatic potential by solving the self-consistent Thomas Fermi-Poisson equation. So, and in solving this self-consistent equation, we can include the effect of all the gates, the left gates, the right gates, and the back gate in the problem. And also an important thing is the boundary condition between indium arsenide and the other material. Because when two materials are in contact with each other, the band offset, whether it's positive or negative at the interface, will determine whether electrons will tend to accumulate or be depleted from that facet. So the band of so a precise value of this band offset is important for getting a faithful electrostatic potential profile in this particular problem. So the band offset values for indium arsenide aluminum and indium arsenide vacuum have already been investigated. So here is the result. So we can see that the band offset value between indium arsenide and aluminum is positive, so that electrons will accumulate near the interface between indium arsenide and aluminum. And the band offset between indium arsenide and vacuum is much less, so that less electrons will accumulate at the bare indium arsenide surface. However, the indium arsenide European sulfide band offset is still unknown, although it is very important for our problem. So we extracted the band offset value and the band bending effect for European sulfide in this work. It turns out that, as shown by the green line, so the band offset value between indium arsenide and European sulfide is in between aluminum and a vacuum. That means the electron accumulation at the European sulfide interface is enhanced relative to the bare indium arsenide surface. So this is the first central result of our work, the value of the indium arsenide European sulfide band offset. And in the following work, we will use this band offset between indium arsenide and other materials as fixed value in solving the electrostatic potential self-consistently. Okay, so this summarizes the first part, the method part of this work. So is there any questions?
Yes, I have one.
Yeah.
Superconductivity parameter you consider in the Hamiltonian, have you computed it by some proximity effect from the aluminum to the semiconductor, or have you just used as a parameter?
Which property of aluminum? You mean superconducting proximity effect or the magnetic proximity effect?
Superconductive.
Oh, as I will show later on. So we treat aluminum and indium arsenide on equal footing. So the superconducting proximity effect will, how can I say, arise naturally or appear naturally in our model. I will explain in the following result.
Okay, it's like delta is non-zero only in the aluminum. However, when you complete the calculations, you get it from the semiconductor too.
Oh, yeah. I see. So the delta, the bare superconducting gap is finite only inside aluminum and is zero in the indium arsenide.
Okay, that's a question. Thank you.
Okay, yeah.
And another question, may I ask?
Oh, yeah, sure.
And do you consider inverse proximity effect on the superconductor, that the gaps can be suppressed by proximity with ferromagnetic insulator or with semiconductor nanowire? Do you consider it? Do you solve the self-consistent equation for superconducting gap?
No, so how can I say? So I think the inverse proximity effect from the semiconductor will naturally be included in our calculation. I guess some of the following results will show that. But the magnetic proximity effect between aluminum and European sulfide is not treated rigorously. So we only add an exchange coupling inside aluminum. So for the superconductor, we didn't say solve the self-consistent gap equation for the superconductor. So we just use say, how can I say, free the simple S-wave superconductor model without, say, self-consistently solving the gap, but we self-consistently solving the electrostatic potential in the arsenide.
Okay, thank you for the answer.
Yeah, thank you for the question. So, and I get, so let me move on. I guess some of the question will be answered by the some of the following results. So next we will explore in detail different mechanisms for inducing Zeeman energy in the hybrid system. So we will study two different mechanisms. One is what we call direct effect between indium arsenide and European sulfide, which is modeled by a local exchange coupling term, and the other is a exchange coupling inside aluminum layer due to aluminum European sulfide proximity effect. So first we study the exchange coupling in aluminum and ignore the the other, direct effect between indium arsenide and the European sulfide. So we first focus on the case where there's no such, so such an exchange coupling in aluminum is 0. We fix the gate and thus the electrostatic potential and calculate the band diagram of the hybrid system. So this may answer partially the previous 2 questions. So this band diagram is a function of kz, which is the momentum along the nanowire axis. And the color of the band indicates the degree of hybridization between semiconductor and a superconductor. So which is defined as the total wave function inside aluminum. So when the band is red, it means all of the wave function are in the superconductor. It's a superconducting state. And if it is dark blue, it's a totally semiconductor state. And it can also in between, then it means it's a hybrid state. So let's look at the band structure close at k equals 0. So this is actually a spin orbit coupled band for the hybrid state, because its weight is about half. So if we look at the wave function of that particular state, we see that about half of its wave function is inside indium arsenide, and half of a wave function is inside aluminum. So in this sense, this hybrid state is induced with a finite superconducting gap, delta induced. I guess this can answer the first question asked before. So in our treatment, this proximity induced gap naturally appear for the hybrid state, and its value is proportional to the weight of its wave function in the superconductor. On the other hand, we see this red band structure. It's the superconducting state, like all of its functions inside superconductor. So this the induced gap, or no, sorry, the gap, not induced. The gap is just the bare value delta naught, right? And these say states are other subband mode for the hybrid state. And now we switch on the exchange coupling inside aluminum, and the band structure becomes this. So there are a few observations here. So first, the spin orbit degeneracy point here is lifted by a induced Zeeman energy. So this effect, we call it indirect magnetic proximity effect, because this means the hybrid state is induced by a finite Zeeman energy by distributing its wave function inside the magnetized aluminum layer, although it has no direct contact with the European sulfide in this particular scenario. So this is the way of inducing Zeeman energy for the hybrid state, and its strength is also proportional to the weight in superconductor. And the second observation here is that the gap of the superconducting state is reduced when the exchange coupling in the aluminum is finite. And the reduction is almost linear, which is the typical property for an S-wave superconductor in the presence of a Zeeman energy. So one question we ask now is if this exchange coupling inside aluminum is the only source for inducing Zeeman energy in the system, is it possible to realize topological superconductor in this hybrid nanowire? Unfortunately, the answer is negative. So because both induced superconducting gap and induced Zeeman energy are proportional to the degree of hybridization, so the Zeeman energy is always less than this induced superconducting gap if the continuum gap is finite. So the topological criteria can never be satisfied in this case. So thus it's impossible to realize topological superconductor if exchange coupling inside a superconductor is the only source of inducing Zeeman energy. So this is our numerical result, and a more rigorous analytic proof can be found in this paper. Okay, so this no-go theorem thus motivates us to explore the second mechanisms for inducing Zeeman energy in the system, which is the direct effect. So the direct effect is a magnetic proximity effect between indium arsenide and European sulfide. And here we model it as a local exchange coupling term near this particular two-facet interface. Here we first remove the aluminum layer and consider a bare indium arsenide. And our focus is on how the gate voltages would affect this direct proximity effect. And this is the result. So it's the magnetic proximity efficiency as a function of the back gate and the right gate. So this magnetic proximity efficiency is defined as the Zeeman splitting for the particular subband mode closest to the Fermi energy in the unit of exchange coupling here. So, and equivalently, you can understand it as like how much wave function are there in this shaded area. So we see that this efficiency actually is a piecewise function of the gate voltages, and each piece corresponds to a particular subband mode. So although a particular subband mode closes to the Fermi surface, so we note that although this efficiency is not a, say, smooth or even monotonic function of the gate voltages, a general trend we can observe here is that when you tune the back gate to a more negative value or tune the right gate to a more positive value, the magnetic proximity efficiency will be larger in this direction. And this can be understood by how the wave function is affected by the gate voltages. So for example, here in the cartoon picture, we show the electrons by this purple area. And when the backgate is more negative, it will it will repel the electrons and push the electrons upwards. And at the same time, if you make the right gate voltage to be more positive, it will attract the electrons to the right. Thus, in the end, the electrons will tend to be confined at the indium arsenide European sulfide interface, where the direct proximity effect is the strongest. So that's why there's such a trend in general. We plot several wave functions in this for this indium arsenide here. So these three wave functions are the subband mode when the backgate is close to 0 volts. So you can see that the wave function is spreading almost all over the indium arsenide cross section. And then when the backgate voltage is more negative, like here, these 3 dots, so the wave function will be confined, will be pushed upwards. So this is consistent with our toy model analysis. So, okay, so next, if we want to add back this aluminum layer, So then what is the effective Zeeman energy for this due to this direct proximity effect? So it's actually a straightforward generalization. You only need to add a prefactor which accounts for the hybridization between semiconductor and a superconductor. So here, if we want to make a very rough estimate about, let's imagine that this direct effect is the only source of Zeeman energy in this ferromagnetic hybrid nanowire. So we find for a typical hybrid state, for example, with half the weight in superconductor and a typical value of this efficiency, we find that the minimally required exchange coupling for realizing topological superconductor is about 50 MeV for this local exchange coupling term. This is a quite large number because a very rough estimate between the indium arsenide and the European sulfide proximity effect shows that the best estimation is about, say, 30 milli MeV in our model. So then 50 MeV is quite large number. So it means, so if the direct effect is the only source of Zeeman energy in the system, it's also very difficult, if not possible, to realize topological superconductor in the system. Okay, so this summarizes the second part. So the conclusion is that for either direct proximity effect or indirect magnetic proximity effect, it's either difficult or impossible to induce topological superconductivity in this ferromagnetic hybrid nanowire. And the next, thus we will consider the joint effect of these two magnetic proximity effect and plot the phase diagram, the topological phase diagram of the hybrid nanowire. So here, as I show, I consider both the exchange coupling term. We first plot the phase diagram as a function of the exchange coupling term due to direct effect and the backgate voltage. And we fix the exchange coupling inside aluminum in this phase diagram. So the chosen value for this exchange coupling in aluminum is extracted by comparing the experimental data. You see that we can estimate this exchange coupling term by observing or comparing how much the quasi-particle continuum gap is reduced relative to its bare value. So that's how we determine the value of the exchange coupling in aluminum. And okay, so this is the phase diagram. We see that, so these purple lobes are the topological phase, and this gray area are the trivial phase. So let's focus on these two lobes at more negative backgate. Important information for this is that we see the tip of the lobe, which is actually the minimally required exchange coupling for realizing topological phase in this ferromagnetic hybrid nanowire, is about, say, 10 MeV, which is a reasonable number. So that indicates that so for this ferromagnetic hybrid nanowire with a overlapping geometry, it is possible to realize topological superconductivity with realistic parameters. And then we want to see how this minimally required exchange coupling evolve with the exchange coupling inside aluminum. So in this particular case, these two values are at aluminum exchange coupling being about 0.25 MeV. So we see that when this exchange coupling in aluminum decreases, and the minimally required exchange coupling will increase. Actually, if you compare this value at, say, 0.25 MeV to 0, you find that the difference can be as large as 5 times. So the required exchange coupling is 5 times larger than this particular case if there's no exchange coupling inside aluminum. So this may explain why zero bias conductance peak is only observed in overlapping geometry and not in non-overlapping geometry. So if we assume that we can approximately model this non-overlapping geometry by just turning off the exchange coupling inside aluminum, because there's no more overlap between aluminum and European sulfide, there's no proximity effect between the two. So this numerical simulation shows that it is indeed more favorable to have a overlapping geometry, because it has 2 sources of Zeeman, while this you can only rely on the direct effect, which you need to be very, very strong. So this is how we understand this geometry difference between the two devices, and have a estimate about the possibility of realizing topological superconductor in this ferromagnetic hybrid nanowire. Next, we study the topological phase diagram in terms of 2 gate voltages, the back gate voltage and the right gate voltages, while fixing the exchange coupling in aluminum, in both aluminum and in indium arsenide. So here we didn't we didn't show the dependence on the left gate, because so compared with the right gate, the left gate is less effective due to the screening effect from this metallic aluminum layer. Okay, so this is the calculated phase diagram as a function of the 2 gate voltages. Now we can see that the topological lobes are in the diagonal direction in this phase diagram. So and actually these dashed lines are equal chemical potential lines. The chemical potential is 0 along these dashed lines, because when you say make the backgate more negative, you will increase the energy of your subband mode. And at the same time, if you increase the right gate voltage to a more positive value, you're actually lowering this energy of your subband mode. So along these dashed lines, the gate of the increase and the decrease of the energy is compensated by these 2 gates, so it keeps 0. And we can see that so along these lines, the subband mode can stay topological all the way, as shown in this B. And also the subband mode can undergo topological quantum phase transition, for example, in this A and the C case. This is quite interesting, because in the conventional understanding, when one tunes the gate voltages, it usually changes the chemical potential of the subband mode, and leading to topological phase transition. But here in this case, the chemical potential is not changed when you change 2 gate, but still topological phase transition happens. So why is that? So we can understand it with a simplified criteria. a simplified topological criteria, because now mu is 0, then the criteria is actually the direct comparison between the total induced Zeeman energy and the induced, say, superconducting gap. And a little manipulation of the equation shows that in the end, it depends on this hybridization of superconductor, semiconductor of the subband mode, and also depend on the direct magnetic efficiency eta, and while other parameters are fixed. And it turns out that this hybridization and efficiency will change with the gates. So that will lead to topological phase transition along this equal potential line. So let's look into more details. So for example, in this lobe A, when we tune the right gate from, say, negative to positive, we see that this magnetic efficiency eta does not change much in this change. But the hybridization or the weight in the superconductor dip monotonically when you increase the right gate voltage. And that means for the particular subband mode, more of its wave function now is inside the indium arsenide nanowire, and less wave function in the aluminum. So the direct Zeeman energy will increase because more wave function are inside indium arsenide, and the induced gap is less. So that caused the topological quantum phase transition in this evolution. And second, if we look at this parameter evolution for lobe C, we find that in this case, the W superconductor, the hybridization does not change that much in this evolution, but the efficiency of the direct magnetic proximity effect dominates the change in the hybridization. So it also increases this directly induced Zeeman energy, so there's making the subband transition from trivial to topological phases. So this is a very interesting finding of our work, because we find that the topological phase of this ferromagnetic hybrid nanowire can be optimized by external gating. You can change either the hybridization or the direct proximity effect efficiency using external gate. But here is a little trade-off you need to pay attention to. So for this hybridization, although a smaller value will help to realize topological superconductor, but in the end, the topological gap is proportional to the induced superconducting gap. So you don't want tune it to be too small, and you want it to be, say, moderately small value, say between 0.5 to 0.4, so that it is in the topological phase, and at the same time the topological gap is not too small. So all right, so that's the end of this talk. So so to conclude, in our work, we extracted the indium arsenide European sulfide band offset from RPAS data, and the value is in between aluminum and a vacuum, and it helps the electron accumulation near European sulfide. And second, we find that both direct and indirect effect are necessary for realizing topological phase in realistic devices, and the topological phase can be optimized by external gating. Okay, thank you for your attention.